Hiya nerds, geeks, and science freaks. Welcome to the chemistry edition of Last Minute Science, the revision podcast for all of your A-level chemistry qualms and queries. I'm your host, Baden Brown, as usual, and today we're going to be having a look at Equilibria. Now, this one may be a little hard to follow as a podcast, as opposed to something where someone is writing it out and you can watch, so I will try to keep it more word-based than having you imagine reversible reactions, because obviously that's not very easy. I'd struggle to visualize a reaction in my head as well without writing it down. The essential idea for Equilibria revolves around this idea of a reversible reaction, which you should have come across already at GCSE, or you should at least recognize the symbol that looks like an equal sign, but at the end of each line there's a little flicky bit up, so it looks like there's two half arrows, and this represents that the reaction is a reversible one, so it can happen in either direction. So A plus B can go to make C plus D, for example, but also C plus D can go to make A plus B. The reaction goes both ways. Any reversible reaction will reach what we call an equilibrium under the correct conditions and given enough time. So, what is an equilibrium? Well, essentially, an equilibrium is where the rate of the forward reaction, A plus B equals C plus D, is equal to the rate of the backwards reaction, C plus D, goes to A plus B. So both of these reactions are happening simultaneously, and if they're happening at the same rate, then we have what we call a dynamic equilibrium. Now, there are a couple conditions for us to achieve what we call a dynamic equilibrium, and the first is obviously that the rate of the forward reaction and the rate of the backward reaction are obviously the same. The second is that we have to have a closed system. So this doesn't have to be anything high-tech. We don't need any fancy chemistry equipment here. Something as simple as a closed container would work, but something preventing outside forces or molecules or chemicals from entering our reaction. So something just like a closed container would work just fine. So then the third and final condition for a dynamic equilibria is that the concentrations of reactants and products are not changing. Now, that does not mean that the concentrations of product and reactant are equal, but from our initial reaction, the concentrations of our reactants and our products aren't changing. So there's one really important idea that we need to follow here when answering questions about equilibria, is what we call Le Chatelier's principle. Now, I don't know anything about Le Chatelier, but I know his principle, and you guys are going to need to know it too. So essentially, what this principle states, and you're going to want to learn this word for word, is when a factor is changed, an equilibrium will shift to oppose that change. So when you change a factor of a reaction that is at equilibrium, the equilibrium itself will shift, it will move to oppose, so against the direction of that change. And when we say factor, what we're really referring to here is the temperature or the pressure. So, what happens when you change the temperature or the pressure? Well, it honestly depends on what kind of reaction we have. Now, if you imagine that, if we think back to when you've studied enthalpy before at A levels, you'll know that you can identify from the enthalpy change of a reaction whether the reaction is exothermic or endothermic. Well, that is tied into equilibrium. It'll give you a reversible reaction, and when it's written out, it'll show you the forward reaction, and then if it gives you an enthalpy change, that will be for the forward reaction. So it'll either be exo or endothermic. And what that means is that if the forward reaction is, say, exothermic, then the reverse reaction would be endothermic. So for example, our A plus B makes C plus D. We take that as the forward reaction and say the enthalpy change is minus 50 to go from A plus B to C plus D. That would make it exothermic. So now if we flip that on its head and C plus D goes to make A plus B, that reaction would then be plus 50 kilojoules per mole for enthalpy change, which would mean it would be endothermic. So you can see that reversing our reactions here will flip our enthalpy change, and so we'll go from exo to endo and go from endo to exo. So how does that tie into our changes in temperature and our changes in pressure? Well, we know that changing, for instance, the temperature of an equilibrium will cause our equilibrium to shift to oppose that change. If I do something to, say, increase the temperature, our equilibrium will shift to decrease the temperature back down. Now, you can use a little bit of logic here. If we're in a closed system, say we're in our box, and we increase the temperature inside the box, how can a reaction decrease that temperature. It needs to absorb the heat, or not a very good way of putting it, but give out cold, which is the properties of an endothermic reaction. So if you increase the temperature, that means our dynamic equilibrium will shift to favor the endothermic reaction to lower the heat. And so you can see that now the inverse would be true if we decrease the temperature. If we decrease the temperature and we need to heat our closed system, our box back up, then our dynamic equilibrium will shift to the exothermic reaction because it gives out heat and it'll bring us back to our original conditions. Now it comes to applying this to our reactions, to our dynamic equilibrium. Say we've got A plus B goes to make C plus D, and it is an exothermic reaction, and we decrease the temperature. Well, you decrease the temperature, so the equilibrium will shift to the exothermic reaction, which in this case is the forward reaction, which means we will get more products. We will have a higher concentration of products. So the same reaction, A plus B to make C plus D, if it is then endothermic and we decrease the temperature, what will happen is it'll shift towards the exothermic, so it will go the opposite direction. So we'll actually get a higher concentration of our reactants. So in a question, you may also need to flip this around on its head. So they may give you the equation, A plus B makes C plus D, and it is exothermic, and they increase the temperature. And if you increase the temperature, then our dynamic equilibrium is going to shift to favor the endothermic reaction, which would be the backwards reaction. So you're going to have to flip the reaction around on its head. So it'd make more reactants than it would make products. So your general rule of thumb here is an increase in temperature will cause the dynamic equilibrium to shift to the endothermic reaction. And your decrease in temperature will cause your dynamic equilibrium to shift to the exothermic reaction. And I think if you use a bit of common sense, that's nice and easy to remember. If it gets hotter, the equilibrium will shift to make it colder. And if it gets colder, the equilibrium will shift to the reaction that will make it hotter. Now we get to take a look at pressure. Well, with pressure, it's similarly simple, I like to think. When you slow down and you think about it and you use some common sense, it makes a lot more sense than you might think. So, for example, 1 mole of gas takes up approximately 22.4 decimeters cubed. The numbers aren't important here, so what I just need you to imagine is 1 mole of gas takes up a certain amount of space, right? And in a closed system, we only have a certain amount of space. So increasing moles will increase the pressure. So when we increase pressure in our dynamic equilibrium, in our closed system, obviously the pressure will shift to then decrease. So the equilibrium will then shift to decrease the pressure, which means that we need less pressure, so in turn, less moles, because moles take up space, so the more there is, the higher the pressure. If you increase the pressure, our dynamic equilibrium will shift to the side with less moles on it. And so then you can probably figure that the inverse is true for a decrease in pressure. If the pressure is decreasing, our dynamic equilibrium will shift to bring the pressure back up, which means it will shift to the side of the reaction with more moles. Now, another important thing to note here, and one of the last, is a catalyst. They love throwing in questions about catalysts, so you need to know about a catalyst. So a catalyst is going to speed up the rate of both reactions equally, meaning that equilibrium will be reached faster, so it's more cost effective to use something like a catalyst because we can reach our dynamic equilibrium faster. However, a catalyst will not, and never will, affect the yield of any product or reactant in a reaction, and it will not shift the equilibrium position at all. It will speed up the rate at which the reaction reaches equilibrium, but it does not affect the position of equilibrium, nor will it affect the yield of any product. And that's really important to make that distinction, because that's the question they love throwing out there. How will a catalyst affect this reaction? It's always the same. Speed, so catalyst, or we got to remember, speed up rate of reaction, equilibrium is reached faster. And the last really important thing to make note of is sometimes using the maximum pressure you can or the maximum temperature you can is not the most cost-effective way to perform the reaction. For instance, say you have a reaction and you're trying to get it to shift to the right, so to make you more products. And it is an exothermic reaction, so you need an increase in pressure to shift to make more products and a decrease in temperature to shift to make more products. But Having a really, really, really high pressure and having machinery that can do that is very, very expensive. So obviously it's going to cost more money, and if you're trying to make a product here to sell it, that's not always the most cost-effective way. So there's a middle ground of high pressure so that you get a higher yield, and low pressure so it's not as expensive. So you're not using the maximum possible pressure for maximum yield here. You're using what's most cost-effective. And a similar thing for temperature, because we need to decrease our temperature. That means we'll lower the temperature to get more yield. But lower temperature naturally means that the rate of reaction is going to be lower, which means it's going to take much, much longer for equilibrium to be reached. And when it takes longer for equilibrium to be reached, we're taking longer for it to make our products, which means it's going to take longer before we can sell them. And we could have made, who knows, maybe 3, 4, 5 more batches of product before that it gets to that point, which means that's also not the most cost-effective way to do it. So there is also a temperature that is the most optimal for keeping the temperature low to get a yield of product and keeping the reaction fast to get it coming through at a steady rate. So it's just important to keep in mind that sometimes the highest possible pressure, say for a product of an exothermic reaction, or the lowest possible temperature is not always what is used because it's sometimes not the most cost effective. Anyway, that is all from me on Equilibria today. Good luck in your A-level exams and keep on smashing your revision. I'll see you in the next one.